Introduction to whole numbers. So, why is counting important?
Well, I mean, it was basically since the pre-dawn of history, right? There's evidence that shows that cavemen had this tally system that at least showed that they kept count of something on a bone, just little marks. So they at least had that idea. I mean, this is 15,000 BC, and then it progresses into agriculture, progresses into the ideas that once we started civilization, right, we started needing this idea to keep count of things.
Keep track of stuff.
Yeah. So shepherds would be out in the field. They would take pebbles for however many livestock they had, right? There was no real number sense to the word. There was no actual like 1, 2, 3, but there was like this pebble represents this animal. And then that's how they kept track of animals. And then it just slowly progressed into something more and more complex, more and more complicated, which is super cool.
I think so. So, for example, we can go and count the number of times the letter T occurs. So the whole purpose of this is to show that counting is kind of a natural thing that we do, right? So we all know how to do this, hopefully, right? So I see 1, I see 2, 3, 4, and 5, right? So we can assign the number 5 to how many T's there are in that random string of letters, okay? So that's just the basics of counting. But you'll notice that when I started counting, I started with 1, right? It's kind of our natural way of doing things. Like we have our fingers and we can count on our hands. 1, 2, 3. So that brings up the idea of types of numbers. So whenever you start thinking about the basic stuff, when you first start learning how to count, that's very natural to you. That's the idea of natural numbers. 1,
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
blah, 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 right? So it just keeps going, right? You can keep going that way. It's a very natural progression of things. Okay, and then we have the idea of whole numbers. So they're not really different.
They're unique. It's a unique set. It's just it's got the idea of 0, right? So the idea of the difference between a natural versus a whole is the whole number includes this idea of 0, something that's not natural at all. You don't see this ever. It's not something that's very concrete, right? That's an abstract idea. Having nothing is concrete, but the idea of the representation of having nothing.
Yeah, if you're thinking about just counting how many dogs you have, you don't start with 0.
Yeah.
0, where are you? Right? You don't do that. Okay, you start with 1. And so the idea of whole numbers, we're introducing the idea of 0 because it's useful. It's a useful number, and we'll get to more and more complicated looking numbers later. Oops, wrong thing. There we go. Complicated looking numbers later. But for now, we're still focusing on whole numbers. So 0 and all the rest of the counting numbers, right? These are our counting numbers. All right. So let's talk about order, right? There is a sense of order among these things. So if I said 4, I could be talking about, 4 circles here. And if I said 3, I could be talking about 3 circles. And if I said 7, let's go purple here. 1, 2, 3, 4, 5, 6, 7. Okay, so now I have a group of 7. So if I wanted to put them in order, maybe I'll go, all right, we'll put 3 first because that's the smallest. And I'll put 4 second. And then I'll put 7 third. Okay, so there's a sense of order here. We go from smallest to largest.
Yeah, but order is very vague in the sense mathematically, so we can actually switch it around. And we can go biggest to smallest. We can actually say 7, 4, 3.
So yeah, okay, so we said order. And we went from smallest to largest. I didn't specify what order to put them in, right? I guess that's true. So I could have gone. I don't know if I could do this. Let's see. Can I flip it? I messed it up. Well, I flipped it at first, but then I messed it up. Okay, well. Hey, there we go. All right, look at that. So nope. We're back to where we were.
You're just a mirror image there.
You know what? We're going to try one more time. There we go. Okay, so largest to smallest. It is in order. Now, that's not the order that we usually are talking about whenever we say put it in order, but it's true.
Order is a very vague word. So mathematically, when we get more complex, we're going to be using these little words that make it more concrete to us.
Yeah, and these are both these are both manifestations of the word order. We just specify what type of order after the fact, right? But order on its own means that we have some rule to put them in a certain arrangement. Okay? And And so order is important, right? As far as, well, where do we go from here? Let's attach this idea to a number line. So maybe you know about number lines at this point. Here's a number line of the whole numbers, starting at 0, goes up to 8, and continues on forever, right? That's what that arrowhead means. If I wanted to, I could say, all right, well, here is 4. Let me try to keep those colors the same. So this was, I think 4 was, I don't remember what 4 was. 4 was red. Okay, so we're going to go with 4 is right here. 3 is right here. And 7's over here. Okay, and so if I'm trying to put these in order, let's say from smallest to largest, we would say 3, 4, and 7. We can visualize that here by seeing that 3 is furthest to the left, then comes 4, if we're going from left to right, and then comes 7. So we could say 3, 4, and then 7.
Yeah, so as you slowly get away from 0, you're getting a bigger and bigger number. So the idea is it's increasing.
All right, smallest to largest. All right. So we have 4 major operations. Okay. Now that we talked about numbers in general, whole numbers, let's talk about the operations on those numbers, right? So you have some numbers. What can I do with them? Well, the 4 main things is addition, subtraction, multiplication, and division. Okay, and so these are not complicated topics. We've seen these for a long time. If you have, 3 circles and your friend has 4 circles and you want to know how many circles y'all have all together, well, that's a simple addition problem right there. You can count them one at a time and you'll see that you have 7, right? You have 7 objects. That's addition. Well, subtraction is quite similar, except instead of adding things in,
I'm taking them away.
yeah. So you're like, oh, you don't get to play with my 4 circles anymore. All right, now, so that would, well, I guess I should write this down, huh? This was 3
Yeah, that was 3 plus 4.
4
That was going to be 7 minus 4.
gives me 7. This one was 7 minus 4, and that gave me 3. Right, so subtraction's taking things away. Okay, at least for now. Multiplication is just shorthand addition. So let's say that you have several friends now. If you're so lucky, you have 1, 2, 3 circles. Your friend has 3 circles, and his friend has 3 circles. Okay, well, how many circles are there all together? Well, this is a situation. Let me do one more. One more set of friends. One more friend, I mean. There we go. So this is 3 times 4, right? We have 4 groups with 3 in each group. There's a total of 12, right? It's the same thing as adding 3 4 times. Okay, so same thing. Division, on the other hand, is like saying, okay, well, you have these 12 circles.
Massive things, and you want to split them.
Yeah, you want to just divide them up evenly. I guess I shouldn't have drawn them so neatly together, but there we go. We have them, and I want to split it up to where everyone has the same amount. Okay, let's say I want to split this into 2 groups. Okay, well, I could say, all right, well, we got 6 right there, and we have 6 right there. So that would be a situation where you have 12 split into 2 groups, right? I don't like the division symbol, so with that. All right, so 12 into 2 groups is going to be 6.
Now,
6 per group.
I mean, you can do it differently, right? You can just draw it around the first 6 and then draw it around the second 6. It doesn't matter
Like
like that. So again, it's however you see these things. Whenever you're breaking them apart, whatever's even in your mind works as long as you hold true to the splitting in even parts.
Let's also, while we're at it, let's say divide it into 4 groups, or let's go 4 groups. So there's a group, there's a group, there's a group. So we took the 12 and we are splitting it into, I guess we could say 3 groups. There's 4 in each group. Another way we could actually word that, different question we can get from the same picture, is you can have 12 split into 4 groups. That's going to give you, 4 from each group. That's going to give you 3 groups of 4. So the first one here, this one's saying that you have 12 items and you're splitting it into 3 groups. There are 4 in each group. this one here is saying that you have 12 items and you're splitting, you want to make sure that each have 4 in each group. How many groups are possible? There are 3. Okay, so both of them, this is a matter of interpretation, but that's basically the basis for division. Okay, now what about commutativity? So that's a fancy sounding word. Basically, that just means that the order that you do the operation in doesn't matter. Okay, so let's go back to 3 plus 4. I don't remember what the numbers were. Let's go 3 plus 4. All right, that is 7.
4 plus 3 is 7.
Also 7. So it turns out the order that you do the addition doesn't matter. Okay, what about with subtraction? Well, if 4 minus 3 is 1, is 3 minus 4 also 1?
Not necessarily.
Not so much, right?
No.
So we would say that addition is commutative
Subtraction's not. Nope.
and subtraction is not. Blah, 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 blah. Okay. What about multiplication and division? Okay, well, let's test it out. 2 times 6 is 12.
And 6 times 2 is 12 as well, so that one works.
All right. Check. That one is a commutative operation. Division. 6 divided by 2.
3.
And 2 divided by 6.
No.
Definitely not 3, right? If I have 2 items split among 3, or split, 2 items split among 6 people, you're not all getting 3 slices of pizza, right? Sorry. Okay, so commutativity. Does the operation give you the same answer in either direction? All right. Prime factorization. So here's another big topic. Prime factorization is important. You're going to get to some problems that are more complicated if you don't know how to do prime factorization. If you can think about 10 instead of as just 10, you can think about it as what times what gives you 10. That actually was more helpful than it sounds. Okay, so commonly what we'll do is do what they call a factor tree, right? And so the question is, what times what is 10? Hopefully that pops in your head right away. Maybe not, but hopefully it does.
1 times 10.
I knew that was what you were going to say. Absolutely knew it. Okay, that's not breaking it up. Okay, so the idea is to get
A prime.
prime numbers.
What's a prime?
Simple numbers.
What's a prime?
What's a prime number? Okay, 10 is not a prime number because, well, I have other options. Okay, 1 times 10 is the only option. No, there's also 2 times 5, right?
Yeah.
So if 2 times 5 gives me 10 and 1 times 10, I have multiple options. It's not a prime number. Okay, prime numbers only have, for example, 2 is a prime number. Let me just say it that way. 2 is a prime number because the only way I could split that up using whole numbers is 1 and 2, right? And that's not splitting it up, actually, at all. That's not making it easier because notice 2 is there. So if I went to split this up again, I'm stuck, right? I'm going like this is forever. So it's a prime number. 1 times itself is the only factors, the only 2 numbers that multiply together that give you that value. Same is true with 5, right? We can't split that up. So 10 is the product of 2 times 5. 2 times 5 is the prime factorization of 10.
So 2 and 5 are prime numbers, and then 10 is what we are known to be composite. So it's built of these prime numbers. So we took something big that's made up of primes, and we broke them down to just simply the smaller numbers, the prime digits.
The prime digits, right? So that makes it 10 is a composite number, right? And then 2 and 5 are prime numbers. Okay, 30 is also a composite number, but we can split that one up.
Yeah, in different directions. 2 and 15.
Okay, so let me do this in multiple spots. So we have 30, and I'm going to do 30 here as well. 30 is 2 times 15. My actual first thought was 3 and 10.
Oh, 5 and 6.
Okay, 5 and 6.
Do another one.
Let's see. All right, if we can fit it right there. Yeah, we'll fit it. 5 and 6. Okay, 2 is a prime number. 15 is not. 15 is 3 and 5. So 2, 3, and 5. We've done reached the end of our tree, right? The branches have ended on prime numbers. 3 is a prime number. 10 we just talked about is 2 and 5. Both of those are prime numbers. 3, 2, and 5. 5 is a prime number. 6 is 2 and 3. Okay, so 2, 3, 5.
2, 3, 5, 3, 2, 5, 5, 2, 3. Again, that idea that commutative properties coming back into play. It doesn't matter the order that we got our primes.
Right, so multiplication is commutative. All of these are the same thing, right? So we could say that the answer is, any one of these actually would be the answer. I'm going to go with this one, though, because they're all in order from least to greatest. But these are all equivalent. Okay, and that brings up the last item we need to talk about, which is one more problem, and then we're going to leave it from there. So 5 minus 7. I know you can't do it, right? That's what they always say, at least whenever you're like in what, second grade?
Yeah, that's what I was told.
Third grade, right? You can't do it. Okay. Of course, we learned eventually that was a lie, right? And let's think about this for a little bit. Okay, you're at the beach. Yep. Probably a terrible example. Whatever. I'm gonna try to draw a straighter line than that. Whatever. Okay. And then you are walking up onto a pier, right? So you're gonna go up one step, 2, 3, 4, 5, right? So now you're on this pier. And then you're going to walk across the pier, and then you're going to start walking down. Okay, so I'm going to change the color here, and I'm going to go down 7 steps. 1, 2, 3, 4, 5, 6, 7. Did I do that right? 1, 2, 3, 4, 5, 6, 7. Not drawn to scale, ladies and gentlemen. Okay, you might notice something.
Yeah, so like, are we in the sand here, or are we in the water?
Wherever you want to be.
Okay.
Where do you want to be?
I like the water.
Okay, let's go in the water. Okay. So let's say that each step was a foot, right? It was a foot. So you went up 5 feet. And then you went down. Let's write the word up there. And then we went down. Let's do that in red. Match up my colors here. Down 7 feet. Okay, well that brought you down here. Right? So you're under the water now by 2 feet. 2 feet under. Right? So that's what we're going to call negative 2. So we're going to say that 5 minus 7 is negative 2.
But negative 2 is not in the number set.
Oh, that's not a whole number at all. Well then, I guess they have to watch the next lesson.